good evening. We've been hearing a great deal recently about Jupiter and comet collisions, but this evening I want to go very much further afield, way beyond our own solar system, which remember is made up of one star, the Sun, the 9 planets, which the Earth is one, and various smaller bits and pieces. Now, the distance between the Earth and the Sun is 93 million miles. That may sound a long way. It's not very far from an astronomer. Let me give you a scale model. Represent the Earth-Sun distance by 1 inch. On that scale, the nearest star beyond the Sun, which is called Proxima Centauri, would be over 4 miles away. That means that light takes over 4 years to reach us. Light travels along at 186,000 miles per second, and therefore in a year it travels rather less than 6 million miles, and that is known as a light year. So Proxima Centauri is over 4 light years away. The Sun's only 8.5 light minutes away. Now, our Sun is a member of the system we call the galaxy. And the galaxy is made up of something like 100,000 million stars, many of them very like the Sun. And it's a flattened system. And when we look along the main thickness of the system, we see many stars almost in the same line of sight, and that makes up the appearance we call the Milky Way. You may think the stars in the Milky Way are in danger of bumping into each other. Well, they're not. We are dealing with a line of sight effect. So the Sun is a member of our own galaxy. There are other galaxies. There's one you can actually see with the naked eye from here. That is Messier 31, the Andromeda Spiral. Now, that picture was taken with a large telescope, actually Palomar. It is a spiral system, placed at a rather awkward angle to us, so we don't see the full beauty of the spiral. But it's a big system, it's bigger than our own, containing more than our quota of 100,000 million stars, and it's more than 2 million light years away. So we're seeing it as it was more than 2 million years ago. But even that is only a start. Far away in space, we can see other galaxies and other systems of galaxies. And in fact, some of them are so far away, their light takes thousands of millions of years to reach us. Look, for example, at this. Now, there's a star field, and this little object here, indicated by the arrow, is what we call a quasar. And that is immensely luminous and very remote. And it looks inconspicuous only because it is so far away. So we can see plenty of things in the universe. On the other hand, there's also a good deal of material that we can't see. Our galaxy is rotating. The Sun's going around the middle in 225 million years. We call that a cosmic year. And all the other spiral galaxies are also rotating. And the way in which they spin and the ways in which the galaxies move compared with each other indicate there's a great deal of dark material in the universe, dark matter. We can't see it. We don't know what it is. But it is definitely there and is causing astronomers a good many headaches at the present moment. So a tremendous amount of research is going on. And remember, these distant galaxies and quasars appear faint only because they are so very, very far away. At this stage, I'm delighted to welcome to the Sky at Night Professor Richard Ellis of Cambridge University. Welcome to the Sky at Night, Richard.
Hello, Patrick.
Now, first of all, why are you so interested in studying these very faint galaxies?
Well, light, of course, travels very rapidly, but the universe, as you've explained, is very vast. And so light takes an appreciable time to travel the distances from the faintest objects that we can see. And so consequently, we're seeing them as they were a long time ago. Now, that's very useful for the astronomer because this means that we can study the universe as it was a long time in the past. One of the main questions we want to answer is why is there such a rich variety of galaxies that we see around us today? We see galaxies with spiral arms, with lots of blue stars in various orientations. We see also elliptical galaxies, which are red in color and have no spiral features. By studying the universe as it was a long time ago and studying galaxies that are very faint and at large distances, we can try and address the question of how old are galaxies and what are the physical processes that lead to this rich variety of systems that we see around us today.
How do you start going about that?
Well, the basic first test that you can do is to count galaxies on the sky as a function of their apparent brightness. Taking deep photographs and CCD images from the La Palma telescopes, astronomers have counted galaxies as a function of their apparent brightness. We can predict how many galaxies we would expect to see if the universe was not changing, and by comparing the observations with those predictions, we can, for example, see whether galaxies were brighter in the past, as some people believe they might be when they're first forming. But really, ultimately, to make progress in understanding faint galaxies, one needs to get the spectrum of the galaxy. The spectrum of the galaxy is very, very fundamental because it tells us the red shift of that galaxy. When we break the light of a galaxy into its spectrum, we see spectrum lines, and these are shifted according to the speed at which the galaxy is moving away from us. This is what we call the Doppler effect. And this shift depends on the distance of the galaxy. Hubble found many years ago that the more distant a galaxy is, the more the lines are shifted to the red end of the spectrum. So, for example, the nearby galaxies are not particularly shifted, but as one goes to more distant systems, the redshift gets larger and larger. And by measuring this redshift, which can only be measured with a spectrum, we can determine how distant a galaxy is, and that enables us, for example, to determine its luminosity. But also, from the distance, we can determine how long light has been traveling to us from that galaxy, and hence at what stage in its history we're studying it.
What about this so-called dark matter?
Well, of course, we can't see this dark matter directly with our optical telescopes, but what we can do is infer its presence from the motions of objects. You mentioned the rotation of spiral galaxies. If one looks at clusters of galaxies, for example, the nearby Virgo cluster of galaxies, then one can detect dark matter by looking at the motions of the individual galaxies. Again, one needs the spectrum of the galaxy and the redshift, which is, of course, due to the velocity due to the Doppler effect. But in this particular case, the Doppler effect is made of two components, one from the expansion of the universe and the other from the actual peculiar individual motions of each galaxy. When one analyzes a large number of galaxies in the Virgo cluster, one finds that they're moving around so rapidly that they can only be held together to stop the cluster from flying apart if there's a large amount of material in the core of the cluster, something like about 50 to 100 times more mass than can be accounted for by just totting up the light from the individual galaxies.
Then, of course, we come to the question of gravitational lenses, the way in which light is distorted when it passes near a massive intervening object.
Yes, well, I think gravitational lensing now offers the possibility of a breakthrough in studying dark matter. What astronomers would like to know, as I mentioned, is how much dark matter is there? Is there enough, for example, to stop the universe expanding ultimately and maybe even lead to it recollapsing? We would like to know, where is the dark matter? Is it distributed in exactly the same way as the stuff that shines? And allied to that is perhaps the most vexing question of all, and that is, what is the dark matter? What's it made of? Is it made of material like atoms that make up you and me, or is it something more mysterious? Now let's have a look at how gravitational lensing works. Normally, of course, when we look at a distant object with a telescope, its light rays come towards us in a straight line. But if there is an intervening object, it doesn't have to be shining at all, then it's possible for that light ray to be bent. And this bending is a prediction of Einstein's theory of relativity. We see the observed image is deflected on the sky. It's not in the place that it ought to be in, and that's because of the effect of the intervening lensing object. This was verified as long ago as 1919, when the positions of faint stars were seen close to the solar limb at the time of a solar eclipse. The stars were not quite in the right position, and this was because of the effect of gravitational lensing. The shift was exactly the amount that was predicted by Einstein's theory. Now, in the cosmos, gravitational lensing is most useful when it occurs in a cluster of galaxies. As I've mentioned, these are very massive systems, and when we look at very distant galaxies seen through a rich cluster of galaxies, we see a wide variety of manifestations of gravitational lensing. What we see depends rather on how close that background galaxy is aligned to the foreground lensing cluster. And in this illustration here, you see that a source on the left is located in the position in which it would lie if there was no lensing at all. And then on the right-hand side, we see what the observer sees looking through this particular cluster. And you can see not only is there a shift in the location of the image, but it's slightly elongated, it's distorted. And this distortion depends on the degree of alignment between the background source and the lensing cluster. And as it becomes closer aligned, one sees gross magnification, what we call giant arcs, and even multiple images where one sees 4, 3, 5 images of the same source in different parts of the sky.